Today I'm going to have a brief discussion about nuclear fission. I'm sure that a lot of you have probably talked about, discussed, or in the curriculum at one point for physics or whatever the case is in college, if you have a technical degree. We're going to talk about nuclear fission, namely where the energy released in nuclear fission comes from. A lot of people have issues conceptualizing this, particularly because of the way it's taught in textbooks. It's very confusing. It's not typically a good way to think about it, although it is convenient for calculation purposes. Alright, so traditionally, nuclear fission, what do we have? Well, I'm sure a lot of you, if you're watching this video, know the basics. We have a uranium-235 atom, right? Massive uranium-235 atom, which absorbs a neutron, becomes excited into uranium-236, and then fissions due to the deformation of the atom into its two fission products, which in this case we'll just say it's, I don't know, barium and krypton, right? Those are two common ones. In this case I think we'd have three neutrons released as well, which is how the chain reaction continues on. So 3 neutrons would be released with energy. The question is, where does this energy, this kinetic energy of all these components come from? That's what we're going to talk about. Traditionally, this is explained using the famous binding energy per nucleon curve, which if you have a textbook that discusses this, I almost guarantee you it's in there. It looks like this, right? And it says 60 iron is the most stable configuration for our atom. It's iron. Okay. So we have uranium-235 over here in the curve. And it goes ahead and says that the binding energy increases between uranium-235 as you go towards iron. I.e., you break this apart, you fission it, you gain binding energy. Okay, so that's the traditional explanation. You go this way, you gain binding energy. First of all, binding energy is the point of confusion for a lot of people. What is binding energy? Well, if you remember, or at one point in the book it probably alludes to this, binding energy is the mass deficit in energy terms, okay? So between the uranium-235 atom and the components, the mass actually decreases, almost magically. Between here and here it decreases, and that decrease of mass, if you made it equivalent energy, is actually the energy that's released. So there's a difference in mass between uranium-235 and the components, which you would think would equal each other, but they don't. All this weighs less than this. And that difference in mass, using E equals mc squared, Albert Einstein's famous equation, which relates energy and mass, is actually the mass deficit, which is the binding energy. So binding energy equals mass deficit for all intents and purposes. They're the same idea. Defect. I call it deficit. I think that's funny. It's actually called mass defect. Okay, so they equal each other. This is just in energy terms, this is in mass terms. It's the same idea. The loss between here and here is the mass defect, or binding energy. So, binding energy per nucleon increases as you go towards iron, which is the most stable configuration. Iron being the most stable configuration, of course, because of the geometric principles of building an atom. There's a maximum radius based on the strong force, which is stable, blah, blah, blah. That's not important right now. But just note this is the most stable configuration. Okay. So, people get confused. They say, well, if binding energy is increasing, why are we releasing kinetic energy? Well, binding energy, right, is not an active energy. Okay? This is not the energy which is continually binding this uranium-235 or these components. It's the energy released. It does equal the energy released when you form that atom. So when you form a uranium-235 atom, the binding energy is the energy that you lost from the components you took to make it when you made that atom. So the change in binding energy is the energy that's released between the uranium-235 and the components. So when you formed these out of this, you released energy, difference in binding energy, as a result. So this is not, I repeat, binding energy is not the energy which is actively holding this together. It's the energy that you lost when you put it together in the first place. And that's a point of much confusion. So this is the traditional explanation. But it still leads people to ask where and why this happens. Okay, so part two, we just learned that binding energy is not the energy holding a nucleus together, but rather is the energy that is released when it is formed. Okay, but that still doesn't answer the question, why is it that when you move towards the most stable configuration of iron, energy is released through fission? That's still not answered. That's not explained with any other way except for in terms of binding energy in any textbook. Now we're going to get into reason why energy is released as you move closer to iron. So, what the textbook probably says is that since the mass of the components is less than the mass of the original atom, energy is released and that matter is converted into energy. Okay, true. Okay. Part two. So we just finished learning that binding energy is not the active energy binding nucleuses together, but rather the energy which is released as the atom is formed. Okay, now we have to explain why it is that this energy is released as fission happens. Most textbooks will explain it simply in terms of binding energy by saying that there's a decrease in mass between the original uranium-235 atom and the components, and that decrease in mass is converted to energy. Mass is lost, energy converted, that's the kinetic energy. Okay, that doesn't explain what's actually happening though. In order to explain the actual energy being released, and it's true that mass does decrease and that change in mass is the energy released. That's a true statement, but in order to explain that, we have to remember that the nucleuses are not made up of billiard balls, right? Nucleons, which are each component, a proton or neutron, are not billiard balls. They're not just balls that are held together. They're actually getting into subatomic physics, or particle physics. They're actually called hadrons. The hadron is composed of 3 quarks, which are held together by gluons. Right? So these are our gluons here. We have 3 quarks of different flavors, but that doesn't really matter for this discussion. 3 quarks, which are held together by gluons, which constitute a nucleon. So this would be, say a proton or a neutron would be comprised of 3 quarks and gluons holding them together. Now, the interesting fact is that the gluons, the energy of the gluons, is the majority of the mass of that particle, of that neutron or proton. And that is that the energy of the gluon is about the mass of the particle. That's where it comes from. Alright? So these are not fixed masses. The more energy that the gluons have holding the quarks together, the more or less, relatively speaking, the hadron, mass, proton or neutron is going to weigh the mass of it. That's determined by the energy of these gluons. And the energy of these gluons are reactionary to the configuration of the atom. So in the case of iron, which is the most stable case, these are actually at the lowest energy level, which means that they have the smallest mass, which means that per nucleon they have the smallest mass. The most mass has been given up, the highest binding energy per nucleon. The most mass has been released per nucleon. They are at the lowest energy state, which means that iron would be the ground state. That's the bottom. So now to bring this back home, to really drive it home for the purpose of understanding, change a piece of paper here. You probably remember doing well diagrams, energy potential well diagrams in college for like electrons or chemistry or whatever the case may be, where you have negative potential energy wells. Well, iron, the most stable form, has the lowest potential energy. Iron is the lowest energy state atom that we can make, which means that the gluons are at the lowest energy state. which means that they have released or relinquished the most energy to form that iron atom. Okay. Now uranium's up here. It's a much more excited atom. The gluons are working much harder to hold the atom together. They're at a higher energy state, which means that there's more mass or more energy per nucleon, right? Which is actively tied up in the atom. It hasn't been released like it has in iron. It's less stable. It's an excited state of the nucleus. So this is our uranium. And when you fission this, it breaks into two components with smaller potential energies, whose components actually add up, this would be the krypton and barium, whose components actually add up to be at a lower energy state. This would be the components, or fission products, whatever you want to call it. They're at a lower energy state than uranium. So what does that mean? What this means is you have your uranium-235 atom, which fissions and sheds energy. It's at an excited energy state because the gluons are at a higher energy state, which means it's got more mass, more massive per a nucleon. It sheds energy by fissioning to two particles of lower gluon energy states. So the nucleuses are at lower energy states, so it sheds that excess energy. It sheds that excess energy as kinetic energy. And the gluons drop to a lower energy state. So essentially energy is shed by the quantized de-excitation of gluons within the atom, which is turned into kinetic energy. And the reason that we see mass decrease is because gluons constitute the mass of a particle. So the gluons lose energy, they lose mass, the particles lose mass. And that's exactly how that process happens. So next time you hear fission discussed in class and you get a little bit confused, or one of your classmates gets confused, you can tell them that it's a simple process of subatomic particles, gluons, dropping an energy state, which releases energy and drops the mass of the particle. It's got nothing to do really with binding energy. That's just a convenient way to do calculations. Thanks for watching.